So, the marbleadder, you wonder what that is. So, this was a project for the Science Festival in Luxembourg some years ago. So, something about me, who doesn't know me. So, my alias is Gunstick. I'm currently president of Syndicate, who manage the level 2 hackerspace in Luxembourg City and is also organizing Hackathon. So what is the idea behind the marbleadder? This was for the Science Festival, and we wanted to do something easily understandable for all ages. And the idea was to show how computers work internally by using a calculator operated by marbles. And this is first idea was, oh, let's build it with Legos. We have big boxes of Legos at the space, so let's build it with that. So what will be taught? What is binary? How computers calculate? How all those logic gates work and how they are combined? And how you can do bigger calculations with just some basic logic gates. So there's an easy and reality way of doing things. So I showed this video. That's the one. Okay, it has no sound because I didn't plug in the sound.
There's no audio, so all you can do is increase the volume of your laptop.
Yeah, volume. I have more volume here. Sorry.
Do you care about the audio?
Okay.
This is accomplished by the rocker rocking one together and dropping the one marble.
So this uses basically.
If I add yet another one to this, we have a 1 plus a 2 or a 3, and adding yet another one to this will cause it to carry twice onto a 4, as follows.
So that's the classic way if you look for marble adding machines on YouTube. You get something with flip-flops. If you implement flip-flops as electronics, you are using a huge amount of transistors. So in reality, computers don't work like that. Well, now they use something. Remove my browser. Computers use logic gates. 3 different ones. Pointer, an XOR, an AND, and an OR gate. With all this, you can build logic gates. So this is a scheme of a 4-bit adder. I've blown it up on the right side a bit. So we have A0 is first bit of variable A, and B0 is the first bit of variable B. With the XOR, you create the sum of those 2 bits, and with the AND, if both bits are 1, you create a carry which goes over to the next position. So you only need 3 operations. And now comes the thing, you have to implement that in mechanics so you can visualize how it's going to work. An AND, XOR, and an OR. And for that, if you watch here, signal A0 goes to the XOR and to the AND gate. So if you do that with marble instead of electrons, you have to have 1 marble coming in, which represents a bit, and it has to go to 2 gates, which is a problem. And we thought a long time about this problem. So that's called duplicating the signal. And we have something, a marble comes in and actionates some lever thing to do the calculation. And of course it has to be synchronized in some way. so it does nothing in reverse. So we built Lego prototype. So that's the end gate. It has a one result only if there are two marbles coming from the top. So one marble on the left goes like that. At the bottom you see it's still 0. One marble from the right, still 0. And the red levers in the middle, you can also see on the Lego prototype, are moving always sideways. And when you push on both, you get actually a 1. So that's a mechanical implementation of an AND gate. And as far as I know, this is the only place in the world where it has been done like this. All the others do this flip-flop thing and do it. XOR. The photo is a bit blurry, so I didn't have a better one. XOR. So XOR only outputs a 1 if one of those signals is a 1, and if both are a 1, it outputs 0. The XOR output has in the middle 0, and if it's to the left or the right, it's a 1. So I put a 1 on one side, it goes to the right, the other side it goes to the left, and if I push on both, nothing happens. Yay. XOR solved. OR gate, well, that's basically easy. You push this one, or that one, or both. Simple. And that's a Lego version of the OR gate. So you maybe have noticed that this is looking similar. So you can actually overlay both, and you have two calculations in one. So this moves the XOR gate, and both the XOR gate stays and the AND gate moves. And the marble duplication problem is solved. So from that point on, we were quite happy that our machine is going to be success. So that's the logic representation of. You want a picture of the previous one? No. The slides are going online. So this is the basic system of marbles running on logic gates. So, and we want to create like boxes where this is in, and every box has a size and is powered by gravity. So we have the XOR gate on top, and then we have a half adder with an XOR and AND on top, another half adder with the same thing, and an OR at the end, which makes a pi of I. And we build that in Legos, so just by pushing by hand. So we have the first half adder with an XOR and AND, second half adder, and the OR is behind. Which didn't work. Okay, you push on the lever and then you hope, and with grease and pulling. The principle worked, but it was impractical that a marble of some grams is going to operate this. And then some theory to get rid of the OR gate. So we are adding, the OR is getting results from A and B, and from A XOR B and the carry. And if you check the logic table, there's never a 1 in both columns. So basically, if you operate this with marbles, there's either a marble coming from the A and B, or for the A XOR B, and never from both. So you never have a problem of two marbles being on one single track and having 2 bits going into an input gate, which results in an OR gate being basically 2 tracks for marbles running into one, which simplifies the OR gate being this bit to this. So we had another idea to solder the stuff. So we get some copper, and yeah, a marble is present is a 1 and no marble is a 0. And also we didn't have so much budget, so copper would be a solution. And we had a prototype.
Which is one of the components of our mechanical calculator. A half adder is combined with another half adder in order to make a full adder. And the full adder we can add with some logic to make the full addition, full multiplication calculator. The half adder is composed of an AND gate and an XOR gate, an exclusive OR gate. The AND gate works when both of these buckets are pushed down at the same time, and we see that one ball from the bottom falls. The XOR gate happens when one or the other is pushed, and we'll see that the ball on the side falls. So in one, this one comes down, and likewise with the other, only this one ball, the AND gate, stays unused. So if we just recharge that, oops. Okay, so what happens when we let go of both at the same time? There's one at the same time, so it's an OR gate that's trapped, XOR gate that's trapped again. So both at the same time, you see that the end falls. And there are a couple issues with the angles of these things, and otherwise we have an XOR gate, which clearly is a tiny bit of a
It's a prototype.
Of course, it's all made out of copper wire, so we have a little more to go to make it perfectly repeatable. We just have to bend the wires, but clearly you can see that the basic concept works.
So we go to building. The idea is to have a frame of some thick copper wires. So that's basically, you go to the shop, buy electrical wires, remove the plastic coating, and you have copper. Buying just new copper wire is not the same. Or it could be horribly expensive. So this is all electric wire transformed into an adding machine. So this is one unit, that's a half adder with the most important part, is this. So you see the levers here, which I showed previously, and the magnets are pushing on top of here, and the results are going out here and here to the side, which is not yet finished. And after we build several of those units, they have to get put together. So we learned how to do spirals. There's a YouTube video for that. And we had a rig built up to put each half adder on the right height to adjust the pieces. So every half adder is basically exchanging in position, and it's always repeatable. This is also to instruct people that you build one chip and then reuse the same chip multiple times to build bigger machines. To explain this computer chip integration. So we had 10 people for 3 months with a whip working, building this thing. Chain fabrication, some people build straight tracks, others build curved tracks, and others build the logic gates, and we managed to get ready for the science festival. Video time. Oops. I just hit trackpads. That one. It's huge, huh? So that's the input data. And the clock releases all input bits at the same time and loads the data into register A and B. So I stop the clock there so you can watch the stuff running down. So all registers are now loaded in the first pile of half adders. And here comes the clock. And now it goes quite fast. we have a result. 0, 0, 0, 1, 1. Seems to calculate correctly. Yay. So this machine still exists. It's just 10 kilometers from here in the hackerspace. If people want to go watch, we can organize a small car trip of about 1-2 hours to really see it live. I repaired it because it got like a bit of desoldering pads and stuff falling off. It needs love. So, yeah, if you are interested in why does it do this? Any questions?
Those coils are for timing? For the timing, for the delay, or?
Yes, they are, but they were not planned.
Okay.
We just put them in, so that we had to go vertically down. Okay, let's do coils. And the timing is extremely tight. So you have the top half adder creating a 1s result, which goes to the bottom half adder, and at the same time the clock goes down, and the marble comes in, and the clock is already there, it just runs through. So it's extremely tight, but works.
Nice.
We were happy that it worked like that, as we have delay loops and things like that. We kept it like this, and it's fine.
Very compact. It's really nice.
Yeah, we had some cool issues which were solved, and yeah, we are happy with the machine. It doesn't need a lot of grease. It's basically hanging. So the logic paths are hanging. Sometimes they are like a little difficult to move. So it gets some small pieces of grease, not too much. Any other questions? Yeah, okay, thank you.